Welcome to students. So, today we will be looking into the chaotic properties of mixing systems. Now, what we are going to start with, our presumption again is that XD is a compact perfect metric space and XF is our dynamical system. So, let us recall the definition of mixing systems once again. So, we say that XF is mixing if for every pair of non-empty open subset X, there exists an n in N such that FNU intersection V is non-empty for every n greater than or equal to. Now, if I try to see what basically this means, then I am looking into the hitting time sets in UV. This hitting time set should contain everything from n onwards, all natural numbers from n onwards. So, basically I can say that this would be a cofinite set cofinite subset of n. And what do we mean by a cofinite subset of n? Basically this is a subset of n whose complement is finite, right. So, only for finitely many things it does not happen, the hitting time does not take place, otherwise you get the hitting time for almost all n, right. So, this is a cofinite subset of n. So, this is a interesting property of mixing systems. Now, let us again recall what do we mean by weak mixing systems. So, let me take XF is weak mixing or weakly mixing if for every pair of non-empty open, and I am taking U1, U2, V1, V2, right, subset of X, there exists an n in N, right, such that your Fn of U1, right, intersection V1 is non-empty and Fn of U2 intersection V2 is non-empty. What does it mean in terms of a hitting set? That if I take this n U1 V1, if I look into n U1 V1 and I look into n U2 V2, then basically I have this n belonging to this intersection of this hitting times between U1 V1 and U2 V2. So, that means that this hitting time is non-empty. So, I take any 4 pair of open sets, right, non-empty open sets, we find that the hitting time is. So, this is what is meant by weak mixing system. And as usual, one can look into the general properties of this system. So, what we have is that I can simply say that factors of mixing systems are mixing factors of weak mixing systems are weak mixing. So, factors of mixing systems are mixing, factors of weak mixing systems are weak mixing. And what do we mean by this fact is that we take up the systems. I have the system XF, right? I have the system YG, and there is a factor in between. So, I can say that there is a continuous surjection from X to Y. So, I have this which intertwines the action of F and G. So, I have this phi as a factor between this factor. What happens here if my XF is weak mixing? So, supposing this is, let me start with mixing first. So, supposing this is mixing, now you start with any two non-empty open sets in Y, right. Then what happens here is you take the inverse image of that, those will be non-empty open in X. Now, in X, since the system is mixing, right, we know that there will exist an N such that from that point onwards, right, there will be always an orbit from one going to the other. So, we know that this we get some N here. Now, again we apply phi to that particular set, right, we again go back over here, right, since this is a factor map, right, it intertwines the action of F and G. So, what we get here is that this also happens to be mixing. So, the factor of a mixing system is mixing, and if we assume our X to be weak mixing, then again we have the same thing, we can take 4 open sets here, then again take their inverse images. What we get here is that there will exist a single N which takes, right, one of them F N of one of them will be going to the other, right, you get the same N, you get the same hitting time basically for a pair of open sets there, and then you are translating it back to this factor, right, what you get here is this is weakly mixing. So, we know that this is basically closed under factors, and also we have seen this earlier that your mixing is a stronger property than weak mixing. So, this implies weakly mixing, and we also know that weakly mixing implies transitivity. This goes in this manner. We have seen clearly that there is a difference between the way we have defined weakly mixing and mixing. Are they the same? So, let us try to understand that using an example, right, and we will try to analyze this example in various stages. But before we try to analyze this example, I would want to actually explain a bit of it, because we have not studied such kind of system earlier, this example earlier. So, now you have already studied the shift space, right, and this shift space what you had studied is that the shift map is a homomorphism. Now, we are trying to look into the one sided variant of the shift map. So, we take our example here. So, maybe we get into this example here, and in this particular example we take our say sigma to be the set of 0 1 raised to the power n. That means, now I am not looking into bi-infinite sequence, I am only looking into infinite sequence. So, this is one sided infinite sequence, and we define sigma from sigma to sigma as, again this is the same thing, sigma x of I equal to xi plus 1. So, the definition of the shift map remains the same. So, you can define the shift map where here when I talk of my x is an infinite sequence, not a bi-infinite sequence, x is an infinite sequence. So, I can write my x to be x naught, x1, x2, x3 and so on. So, this is just a one sided infinite sequence. Now, if I try to look into this manner, I can simply say that what is my, so what is the initial point of x? So, the initial point of x is x naught. What is sigma doing is, the action of the shift map is simply it is forgetting what was in the first place, right. So, it is just forgetting or just deleting what was in the first place, and then whatever remains happens to be your sequence. So, what happens at the nth state? So, what happens here is that my x, right, at 0 is x 0, but what happens to my sigma x at 0? That is x 1, right. And similarly, I can say that what happens to my sigma to the power n at x, what happens to the 0, right, what is the initial symbol here. So, that symbol happens to be x n. Okay. Now, the definition has changed to the fact that we are now going from bi-infinite to infinite sequences, but the rest remains the same. Can we still say that sigma happens to be continuous? What is the topology on this space of sequences? We again have the product topology here. So, again the product topology is given by that metric, right. You can think of the metric, same metric delta ij upon, right, 2 to the power I. Now, we do not need to take mod, right, 2 to the power I. So, you have the same metric there, and under the same metric, under the same product topology, I can say that my sigma happens to be continuous, right. It is not difficult to check, it is the same proof that works out, that sigma happens to be continuous here. But here the difference is that sigma is just continuous, right. It is continuous, it is surjective, but it is not a homomorphism, right, because I cannot define sigma inverse here, because if I try to take sigma inverse, I will have two possibilities, right. Either the sequence could start with 0 or the sequence could start with 1, right, there are two possibilities, fine. So, here sigma is not invertible. So, here I should say that the shift map is not invertible. But is continuous. It is continuous, it is surjective, right. So, this is our shift map here. Now, for this particular shift map, so this is basically called one sided shift, right. So, for this shift map, we now want to look into something else. Now, very easy to check that this shift map will be transitive and so on, right. We also see that this shift map happens to be mixing, fine, because after something is over, right, it is the same proof that works out that this will be also mixing. So, this particular system is mixing. Now, since it is mixing, it is also weak mixing, it is also transitive, that is taken for granted. But now we want to look into something else, and as we have noted earlier, so what we have noted is that we have noted this earlier, that if my y is a subset of x, right, and y is invariant, then y gives a subsystem So, now I am trying to define a subsystem of this particular system. So, I have my sigma sigma, this is my system here, and I am trying to define a subsystem. So, let me take here again we go back to definition. I am taking here P to be some subset of natural numbers. Now, what I am allowing here is that I am taking my set X to be the set of all sequences xi such that xi equal to xj equal to 1, right, if and only if mod of I minus j belongs to P. So, what we are trying to do here is, what is our system X is, it is definitely a sequence of, it is an infinite sequence of zeros and ones, but what are we doing here is that we are trying to look into the system, right, we are trying to look into this system where mod of x minus y. So, that means we are trying to space, what is the space between two ones. So, how many zeros are there between two ones? So, exactly all those elements which belong to P. So, you can place zeros anywhere, does not matter, but where can you place 1? So, you can place 1 only when the distance between two ones, right, is some element of P. Definitely is a subset of sigma. So, subset of all sequences of zeros and ones. Is it invariant? Can I say that sigma of x is a subset of x? Because even if I shift it, right, I am not changing the distance between two ones, the distance between two ones remains the same, right, the spacing between two ones remains the same. So, basically I get the same thing back here, right, and so I can say that this is a subsystem, right. So, is a subshift, or I can say a shift space. And we have a name for this shift because of this being defined using our spacing, because P is in our hands, we take P in our hands. So, we call this system, so this system is also called, this shift is also called the spacing shift. Now, it has various beautiful properties here, but we are trying to look into it from a particular angle. So, now what we do here is, we try to take up an open set here. Now, we know that open set in shift space are defined using cylinders, and in our case the cylinder becomes very simple because only the initial part gives you, any initial word gives you a cylinder, right. So, here we take up U to be the cylinder 0, that means I am looking into all those sequences yi such that y0 is, sorry, I should take it 1 here. So, y0 is equal to 1. Let me start with that part, y0 is equal to 1. So, I am starting with all those things which initially start with a 1. Now, I know that once I start with a 1, right, the next instant will be, the next instant of 1 will be whenever your j happens to be equal to some element of P. Now, also assume so, I also assume that my spacing shift is mixing. Of course, the properties of spacing shift depend on P, right. So, we assume that this is mixing. Now, what does it mean that this is mixing? Then for my open set U, right, there should be existing an n, right. So, what does that imply? That implies that there exists an n in n such that sigma n u intersection u is non-empty, right. Sigma n intersection u is non-empty for all n greater than or equal to n. Now, think of that fact. What are the elements that can come up in sigma n u intersection u? So, if there exists an x belonging to, so basically if x belongs to, or I should say the sequence xi belongs to sigma n u intersection u, since it belongs to u, its first part should be equal to 0. So, that means x naught should be equal to, sorry, its first part should be equal to 1. So, x naught has to be 1, right, and since it belongs to sigma n u, right. That means after nth stage also it should be u. So, that means xn should be equal to 1, right. So, in that case what we have is here x0 is 1 and xn is 1. What are all the n for which this will be non-empty? What are all the n's for which this will be non-empty? Now, my first is always a 1, right, and the next subsequent this will be non-empty only if the nth part is 1, right. So, what are all those n's for which this is going to be equal to, this is going to be non-empty? This is if and only if n belongs to P, right. So, this is non-empty if and only if my n belongs to P. So, what do I know about this particular set? I know that this particular set NUU, it should be a cofinite set, right. So, NUU should be a cofinite set because we are in a mixing system, right. I again recall the mixing part here. So, let me again recall this part, right. So, we say that the system is mixing if this is non-empty for all n greater than n, that means NUU, what I am starting with u. So, your NUU should be a cofinite subset of n, which means that now here my P should be a cofinite subset because this has to be cofinite, right, NUU has to be cofinite. So, my P is cofinite. So, this gives me that P is cofinite. So, what we have observed here is that if my system is mixing, right, if my spacing shift is mixing, it is not an ordinary system, it is basically a spacing shift. So, if my spacing shift is mixing, then that means that my P is, that spacing set, right, is cofinite. And I just want to say that it is not very difficult to observe that the spacing shift, right, which I denote it as xp because it depends on p sigma, this spacing shift is mixing if and only if, right, p is cofinite. It is not very difficult to observe that the converse also holds true, but we are not getting into the proof of the converse part. We just observe here is that if my spacing shift is mixing, then my P has to be cofinite. So, we have another example of a mixing system, and now we know that a mixing system is always weak mixing and it is always transitive. So, we know that this system is weak mixing also, this system is transitive also. So, we try to go into now the weak mixing part. So, again I would like to recall the definition of weak mixing. So, we say that this is weak mixing if for every pair of non-empty open sets U1, U2, V1, V2, there exists an n such that n U1, V1 intersection n U2, V2 is non-empty. Right? That is basically what is meant by weak mixing. To start with this thing, we go back to the wonderful observation which was pointed out by Furstenberg in 1967. So, we go to Furstenberg intersection lemma. This can be attributed to Furstenberg 1967. Now, this used some more mathematical definition of something which is called a filter, but we are not going to use the concept of filter here. So, I will just quickly explain what this means is. So, I said that this system XF is weak mixing if and only if, right, for NUV is non-empty for every pair of non-empty open sets and for non-empty open sets say u1, u2, v1, v2 subset of x, there exists now this is not related to this one, but there exist for this u1, u2, v1, v2 there exist open sets. So, let me again take u and v, definitely these have to be non-empty. Such that NUV is contained in NU1 V1 intersection NU2 V2. Furstenberg had this intersection lemma that basically if you have a weak mixing system, then if you take the hitting time sets, right, of two pairs, you take their intersection, then you will find that the hitting pair sites of a third pair, right, is contained in it. You will always find for any two such things, you will always find open sets u and v such that this is contained inside. Now, we try to prove this factor and the proof here is very simple. So, try to prove this part. Now, think of that part. I am using the if part, right. So, this is if and only if statement. So, if I prove the if part, right. So, if part means if this part holds, then anyway we know that the system is weak mixing, it follows by definition, right. So, the if part follows from the definition. Now, if part follows from the definition. So, what happens for the only if part? We observe that now if I am taking n u1 u2, right, and n v1 v2, then we know that for these two pairs, right, the intersection will be non-empty because my system is weak mixing. So, system is weak mixing, this intersection is non-empty. So, let me take a k belonging to this system, and what does that mean? Right? That means that what I have here is u1 intersection f to the power minus k u2, this is non-empty, and v1 intersection f to the power minus k v2, this is non-empty. Now, these two sets are non-empty. These are open sets also. So, I call this open set as U and I call this open set as V. Now, I have two non-empty open sets and I know that for any pair of non-empty open sets my NUV happens to be non-empty, right. So, let n belongs to NUV. I know that NUV will be non-empty. So, you will always get some n belonging to NUV. So, this happens to be non-empty. What we get here is, so what does that mean? That means that my U intersection f to the power minus n v is non-empty because my n belongs to NUV, right, n belongs to NUV. And that gives me that U intersection f to the power minus n v is non-empty. But what is my U? my u happens to be u1 intersection f to the power minus k u2 intersection f to the power minus n. What I have here is I have v1 intersection f to the power minus k v2. I know that this is non-empty. Now, the same set I can write it as u1 intersection, because this is all intersection, right. I can just take association here. So, this is minus n v1 intersection f to the power minus k, right. I can say that this is u2 intersection f to the power minus n v2. Now, this is non-empty, right. This is the same set, this is non-empty. So, if this set is non-empty, what does that mean? That means that in particular this is non-empty, right. And in particular, because if I am looking into f minus k of this set, right, it means that this particular set is also non-empty. So, that means that u1 intersection f to the power minus n v1, this is non-empty, and u2 intersection f to the power minus n v2, this is non-empty. Now, what does that imply? My n belongs to n u1 v1 intersection n u2 v2, right. And we started with n to be any element of n u v, right. So, basically means that n u v is contained in n u1 v1 intersection n u2 v2. So, basically if I look into the intersection of hitting time sets of two pairs, right, get that it contains the hitting time set of a third pair, right. Third pair is definitely related in that part. Now, try to think of this more broadly, right. If I take the intersection of u1 v1, sorry, of this u v with some u3 v3, right, then that would give me that there is another hitting set contained in the intersection of n u3 v3 with u v, but n u v is already contained in this intersection. That means that I will have another hitting time set which is contained in n u1 v1 intersection n u2 v2 intersection n u3 v3. So, that means now for 3 pairs u1 u2, u1 v1, u2 v2, u3 v3, right, we find that the hitting time sets is non-empty. We could take this up to for any finite n, right. So, what does that mean is, if I look into this consequences here, the consequences are very important here. So, if I look into this consequences here, so the consequences, the first consequence is very interesting. It says that for if I have u1 u2 un, right, and v1 v2 vn, non-empty open, this is non-empty. What is the meaning of that? If I try to look it very broadly, what is the meaning of that? Now, think of that. I am saying that XF is weak mixing, right. Weakly mixing, right, which is same as saying that I am looking into the product of two sets, right. I am looking into the product is weakly mixing, observation says that 2 implies n, right. So, if I take the hitting time sets of n sets, it is non-empty. So, that means that this is same as saying that x to the power n, and now I am writing f to the power n, right. This is weakly mixing, or this is this is transitive, this is transitive. So, that means that this is also, the end product is also transitive. So, 2 implies n, right. So, what we get here is that this is weakly mixing implies this is the product x cross x f cross f is transitive, and that means the end product x n. So, we know that what is x n? X n is basically x product with x, right, n times, and f, now I am writing it in a bracket n because we know we are not looking into the iterate there. So, this is basically f product with f, and this product goes n times. So, 2 implies, so x f is weakly mixing if and only if the end product is transitive. Interesting case here. Now, this is one consequence, and this gives rise to another consequence. So, for that another consequence, let us try to take down a definition here. So, now I am saying that if I have a subset, say let me take k to be a subset of the natural numbers, this is called thick. So, I am calling this set of natural numbers to be thick if it contains arbitrary long segments or it contains an arbitrary long sequence of consecutive elements of n. What I basically mean here is that, now what that means here is that for given any n in n, right, there exists a k in k such that all these elements k, k plus 1, k plus 2, k plus n will belong to k. So, what we have is we have this consecutive elements of n, and that means arbitrarily large consecutive elements will be belonging to the set k. So, this set k is called thick. What we have here is that if my system is weak mixing, so this is the next observation that we are going to have, and let me write down here, we will prove that next page, but I just write down here that this is weak mixing. It's very simple to write if and only if, right, given non-empty open UV subset of X, right, NUV is a thick subset So, this is a thick subset of n. There is another characterization here. So, this is a thick subset of n. Now, we try to look into this proof of this part, and the proof turns out to be very simple here. So, what I have here is that let me start with an open pair U and V, right. These are non-empty open subsets. So, these are non-empty open subsets. Now, since these are non-empty open subsets, I can say that my U, V, F inverse V, right, up to F minus n V, or I should say F, yeah, F minus n V, this is non-empty, right. These are all non-empty and open. What does that mean? If I take my n u v, right, its intersection with n u F inverse V, right, intersection with n u F minus n V, right, this is not empty. So, what happens if a k belongs to this set, this intersection? All it means is that, right, U intersection F minus k V is non-empty, U intersection F minus k minus 1 V is non-empty, U intersection F minus k minus n is non-empty, minus n V is non-empty. And that implies that k, k plus 1, k plus n belongs to n u v. So, take any hitting set, right, the system is weak mixing, take any hitting set, what you find is that this n u v happens to be a thick set. So, this is one of the characterization of weak mixing systems, that this set is thick. Now, let us again go back to our example of spacing set. Right. So, we again go back to our example, spacing shifts. Now, when can I say, now we again continue. So, we continued this example. So, our U was this cylinder set of 1. So, what can we say about n u u? Now, I am assuming that the shift is weak mixing, right. Then in that case, what can you say about n u u? It should be a thick set, right. So, this is a thick set. If my system is weak mixing, now we know that when is this non-empty, whenever you are, when is that particular thing non-empty, right, this would be basically just my set P here, this particular, for this particular U, this is just the case P here, right. So, my P is a thick set. Now, we easily look into the fact that if I have a cofinite set of subset of natural numbers, the subset is cofinite, then the subset is always going to be thick. If subset is cofinite, it is always going to be thick, but you may have thick subsets which are not cofinite, right. It is always possible to have thick subsets which are not cofinite. So, since we have thick subsets, right, we can have thick subsets I just write thick sets which are not cofinite. We have an example of a mixing system which is not weakly mixing, sorry, we have a system example of a weakly mixing system which is not mixing. we simply take this spacing shift, right, with P to be a thick set which is not cofinite, right. So, this example is simply our spacing shift xp, right, with P thick, right, but not cofinite. So, if I take this example of spacing shift, then we know that this will be weakly mixing, this will be weakly mixing, but this will not be mixing, right. So, in general weakly mixing is a what to say, coarser property, right, it is not a stronger, it is a weaker property, and that is why we call it weakly mixing, right, it is a weaker property than mixing. So, we know that we have an example of a weakly mixing system which is not mixing. Now, let us look into some other properties, and we compare this with say minimal systems here. So, we know that this system is minimal, right, we want to compare that with minimal systems. So, all we look into is this, just want to write a theorem here, that an equicontinuous system cannot be weakly mixing. So, an equicontinuous system cannot be weakly mixing. What we want to check out here is that this would always hold. So, start with simple proof here. So, now we know that the system is equicontinuous. So, let xf be equicontinuous. Now, what does it mean by xf being equicontinuous? We know that whenever two points are at distance given any epsilon, there exists a delta such that whenever two points are delta apart, right, their images will be epsilon apart, right. So, let epsilon be given and let be defined accordingly. Now, take or I am defining my epsilon here. So, what I do is take x y1 y2 in x let us take this epsilon, right, such that my distance between y1 and y2 is phi epsilon. Since choosing the epsilon is in our hands, we choose our epsilon such that the distance between y1 and y2 is phi epsilon. Now, think of this part, we take this open set U to be equal to a ball of radius delta, and now with respect to this epsilon we have a delta defined, right. So, we take U to be a ball of radius delta centered at x. We take our V1 to be a ball of radius epsilon centered at y1, and we take our V2 to be a ball of radius epsilon centered at y2. And now, we want to look into what happens. So, let n belongs to nu v1 intersection nu v2. So, we have an n belonging to this thing, that means we are assuming that what happens supposing our system is weakly mixing. Then we know that by equicontinuity since my system is equicontinuous, right, all I know is that diameter of Fn of u, right, will be less than or equal to 2 epsilon, because my u is having diameter delta, right, we know that these are delta apart, right. So, the diameter of u epsilon will be less than or equal to twice epsilon. Now, since the diameter of Fn of u is less than or equal to twice epsilon, all I can say is that supposing I am taking a ball, right, around y1 of radius 3 epsilon, then my Fn of u will be contained inside this ball. We have equicontinuity, right, we have started with a ball of radius delta centered at x, right. So, we know that whenever they are delta apart, the rest will be epsilon apart, right. So, at the most what we have is that the diameter of Fn u, because n belongs to n u v1, right. So, the diameter of Fn u will be less than or equal to 2 epsilon. In any case, it will be less than 2 epsilon because our equicontinuity, it will be less than 2 epsilon. So, that means that this diameter is less than 2 epsilon. So, this will be contained, supposing I start with the point y1, right, I take an open ball of radius 3 epsilon, right, then this entire Fn u will be contained inside that. But what does that mean? That would mean that my Fn u intersection this ball, which is my v1, sorry, which is my v2, right, this would be empty, because my d of y1 y2 is phi epsilon, right. D of y1 y2 is phi epsilon, but what we have is that Fn u is contained in this particular ball 3 epsilon around y1, but then that would mean that Fn u can never intersect v2, right. So, I can never have an n belonging to this factor. Right. So, basically that would mean that n u v1 intersection n u v2 is definitely going to be empty. If Fn u comes, if n belongs to this factor, then n can never belong to this part because of the property of equicontinuity, and so xf is not weakly mixing. We are more interested in the consequence here. So, we try to look into what is the consequence of this part. Now, if I try to look into again, go back to the first part, we started with x u1 y1 y2, right. That means my point of x, right, the point x, right, because if the system is weakly mixing, supposing I assume that the system is weakly mixing, then this point x cannot be an equicontinuity point, because then I would require that my n u1 v1 intersection n u2 v2 should be non-empty. So, that means that this point x that I start with is, right, this point x that we start with, it cannot be an equicontinuity point. So, that means the system has to be sensitive there. Now, think of that part, the system is sensitive there, we are in a compact space, in a compact space every continuous mapping is equicontinuous, right. So, we can always find some sensitivity constant there, right. So, basically the consequence here is that xf is weakly mixing implies it is sensitive. xf is weakly mixing implies it is sensitive, and what we have seen here is that we have minimal systems which are equicontinuous, and for minimal systems which are equicontinuous, these minimal systems cannot be weakly mixing, right. So, equicontinuous minimal systems cannot be weakly mixing, that means that my minimality, right, minimal does not imply weakly mixing, so different property. And again we have this example of tent map, which is not a minimal system, but this is weakly mixing. So, my weakly mixing does not imply minimal. We stop here with this observation and we will continue with the same point, right, in the next lecture.